Kia ora, Year 9. This video follows on from the ones I made yesterday that look at how we go from a fraction to a recurring decimal. So in this one, we're going to work the other way around. How do we convert recurring decimals back into fractions? So there's a wee bit of algebra in these, but usually students find these more fun than the first way around. So I just want to go over again how I want you to do this. When you're doing an example from this video, I want you to make sure that you're writing it out pretty neatly in your book so that you've got some good notes. Okay, and once you finish this, there's a Dr. Frost worksheet that I've set you that you can go off and do. And again, when you're doing those Dr. Frost questions, just make sure you're getting some nice working to record how you do them for when you come to look back later on. So what do we mean again by a recurring decimal? Well, let's start with one like this. Let's find my pen. So suppose we've got 0.2, which we write like that. So that's the same as 0.22222 and going on forever. So how can we figure out what fraction produced that? Now for that one there, a lot of you watching this probably can spot that 1/9 is equal to 0.1 recurring. And so 0.2 recurring is probably going to be 2/9. So we kind of already know the answer, but let's have a look at how we could get there, because the method is going to help me with all recurring decimal to fractions problems. And I think it's pretty cool. So we're going to use a little bit of algebra. We're going to say let x equal 0.2 recurring. In other words, x is equal to 0.222 and so on. But we know that we can write x as a fraction. The trouble is the 2's go on forever. So we want to think of a way that we can kind of somehow truncate all of those excessive numbers of 2's. So let's think about what would happen if I multiplied one lot of this. What happens if I've got 1 times that number? Obviously 1 times that number is just that number. But what if I had 10 lots of that number? Well, 10 lots of that number would be, let's see, well, this place value column here, the 2 is 2/10. So 10 lots of that would be 2 wholes. So that would move to here. The 200ths here would be 2/10. And so on. The 2,000ths would become 200ths. That's if I times it by 10. And we write that as 10 lots of x is just 10x. So now we've got two things that go on forever. We've got one lot of x here, and here we've got 10 lots of x. So if I've got 10 lots of x and one lot of x, the difference in those two things is going to be 9x. Right, so let's write this out carefully. 10x is equal to 2.2222 dot, 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 dot. And we're going to line our columns up quite carefully. So just 1x is equal to 0.22222. So all of the going on forever 2's are kind of matching up. So if we have 10 lots of something and we take away one lot of it, we're left with 9 lots of it. So 9x here has got to be the same as this, take away this. But that leaves me with, look at your place value, 2, take away the 0 is just 2. Now here, 2/10, and I've got 2/10 matching it down here. So that's this. So we've got 9x is equal to 2. So 9 times the number of 2 is 2, so the number is 2 divided by 9. So that's my first example of how we go from a recurring decimal to a fraction, and I've done that really, really slowly on purpose. Now I know some of you are watching and going, oh man, she is so slow with how she does this, but it's deliberate, because now we're going to crank it up a little bit and have a look at some harder ones. So that's your first example. So here's example number 2. This time let's look at a recurring decimal which has got a more complicated pattern. So x this time is equal to 0.131313 going on forever. And again, we need to find a way to match up the place value here by multiplying x by something. So let's look at what we did in example 1. Well, in example 1, we just had to match up all of the 2's. So once we multiplied by 10, all of the place value shifted across one column. But if we multiply by 10 here, we're going to get into a mess. This is what we'll have. 10x will be 1.313131 and so on. X will be 0.131313, and they're not matching up. So when I start subtracting stuff, I've still got something that's going on forever. But you can probably see what's going to work. If I instead multiply by 100 and I get 100x, then I'm going to have 100x. So this 1/10 is now going to become 10. So it's going to be 13.131313. And we've got 1x, which is 0.131313, and so on. So subtracting 1 from 100 leaves me with 99 of the thing. So 99x is equal to 13, which gives me my fraction as x equals 13 over 99. Now this one's pretty easy to see that we're done, right? We can't simplify any further, and we know that because 13 is a prime number. But this type of problem gives you lots of awesome practice at your divisibility rules. And some of you will have played around with those in things like OPS and maths when you were at intermediate and primary. So I'm going to do a trickier one now. Same kind of idea for the recurring decimal to fraction bit, but I want to think about how we can check whether we've fully simplified it. So this is example 3, and this is the last example I'm going to do before I get you to go to Dr. Frost. So the recurring decimal that I'm working with is x is equal to this, 0.1245. And the pattern's got 4 digits in the way it recurs. So let's start by writing that out, just to make sure we've got the pattern down. So here, to match up this 4-digit pattern, I'm going to have to multiply x by a whopping 10,000, right? Because 10,000x will give me 1,245.1245, and so on forever. And one of those x's will be this. And again, because I've got all of this to match, things are going to work out well. So when I subtract one of those x's away from 10,000, I'm left with 9,999x, and that gives me 1,245. So dividing now, we get x is equal to 1,245 over 9,999. And this is where the divisibility rules come in. Now, some of you will have more sophisticated versions of these, but the most basic one that I like looking at with Year 9s is that we can tell if a number can be divided by 3 if the digits add up to a multiple of 3. So 1 plus 2 plus 4 plus 5 is equal to 12. 12 is a multiple of 3. So we know that 3 is a factor here, and we can see just from looking that 3 is a factor here. So first I'm going to simplify by saying we've got x is equal to 415 divided by 3,333. So now we have to look again and say, I wonder if I've simplified that all the way, or if there are any common factors. But if you think about it, we don't have to check really all that high, because if I'm matching up pairs of factors, and we'll do this probably next week when we talk about factors and multiples, I can see that here I'm going to have 1 times 415, right? And then I'm going to have, what else will I have in there? Well, I'm definitely going to have 5 is going to be a factor. So the thing that goes with the 5 will be up here at, what's it going to be, 90, not 90, 83. So if I'm checking for factors of 415, I just have to go as far as roughly the square root of that. So I've got to check up to about 20 or 21, right? Because 20 squared will get me to 400. So let's have a quick look at this and see how I can think about hunting for pairs. So because I only have to go to 20, and because this is a teaching video, I'm going to list them out. So let's just jot down all of the numbers up to 20, and we're going to do some knocking out for what we know won't be a factor. Then we're going to quickly check the ones that are left, right? Because if it's not a factor of this one, then it can't be a common factor of both of them, right? So quickly looking, well, we don't care about 1. This is an odd number, so 2 is not a factor, 4 is not a factor, 6 is not a factor, 8 is not a factor, 10 is not a factor, 12, 14, 16, 18, and 20 are all not factors. We also know that 3 is not a factor because the digits add up to 10, so we can get rid of 3 and we can get rid of 9. Now we do know that 5 is a factor, but we know that 5 is not a factor of the denominator. So we don't care about the 5 or the 15. And we knew the 15 wasn't because that's a 3 multiple. So it leaves me with not really very much to check. And we're going to look at why that is. So this is where your numeracy strategies from primary school come in really useful. We could do short division here as well. So does 7 go into 415? Well, no, it doesn't, because 7 60s is 420, and that's only 5 up from it. So 7's not a factor. What about 11? We can see that 11 might be looking good for down here, but is 11 a factor of the denominator? Well, we've got 440 is a nice round multiple of 11. And if we move down to 415, that's a gap of 25. And this isn't a multiple of 11, so we know 11 is not a factor. We can do the same kind of thing with the other ones, right? So if you look at 13, let's think about a nice round number there. 390 is a multiple of 13. And the gap to 415 is plus 25. So that gap is off, is not 26, right? So 13 is not a factor. And we can do the same thing on 17 and on 19. All right, so what we found is that this is the simplest way to write my recurring decimal as a factor. So we can write 0.1245 as a fraction is equal to 415 over 3,333. There are a couple more pattern types I haven't done. There's one that goes like this. So we might have 0.1247, right? So your repeating part doesn't start all the way back here. It starts out here, but you can apply the same kind of method. I'm going to leave that for you to work out together because I want to leave you something fun to do. Now what I want you to do is make sure you've got some good notes and then hop on to Dr. Frost and do the worksheet there. Now, if you're watching this video before class, can you please not do the Dr. Frost just yet, because that would be awesome. I will never run out of work for you, but sometimes it's good to save a few things to do in the lesson. Thanks for watching.